Hello everybody. So in this video we're going to continue with chapter 14, Integral Calculus 1, specifically section 14.4, area and the definite integral. So we're going to start this video by talking about example 14.17. And it says, find the area a of x, so that means it's a function, between the graph of the function f of x equals 3 and the interval -1 to x. And then it says find the derivative of a of this area function. So this is a rectangle that has a base of length x plus 1. That would be the distance between -1 and the value x here, right? It would be a total distance of x plus 1. So that means that the area is going to equal to base x plus 1 times the height, which in this case is going to be 3. So x plus 1 times 3, and this simply is going to equal to 3x plus 3. So then it says find the derivative. Notice that if we do the derivative of a, it's simply going to be 3, which, by the way, is f of x again. And this is something very interesting that has a lot to do with the relationship between areas under the curve and derivatives. Very well, so next we have example 14.8, and it says find the area a of x between the graph of the function f of x equals 3x plus 2 and the interval -2/3 comma x, and then find the derivative of a of this area function. So this is the x-axis, as you can see here, and notice that the point -2/3 is right here. Why is that? Well, because if you do f of -2/3, notice that it's going to be 3 times -2/3 plus 2, and this is obviously going to be 0. Therefore, -2/3 is an x-intercept. So we have the coordinate -2/3 here, comma 0. Then this is a triangle, and the base of the triangle would be x plus 2/3, right? Because if you have -2/3, that means that the y-axis would be somewhere around here. Therefore, the total distance would be x plus the 2/3. Then the height would be equal to 3x plus 2, which is the function of this inclined line. Why is that? Well, if you plug in x in the function, you obviously get 3x plus 2. So that means that the area is going to equal, because it's a triangle, it's going to be equal to 1/2 the base, which is x plus 2/3, times the height, which is 3x plus 2. So notice something here. If we multiply this by 3, I can do that if I also divide by 3 at the same time. So I'm going to get that the area is going to equal to 1/6 times 3x plus 2, which would be the result of multiplying this expression by 3, and this times 3x plus 2. So we are going to get that the area is going to be 1/6 3x plus 2 squared. The next step is find the derivative. So if we look for the derivative, we will have to apply the chain rule. And notice that it's going to be equal to 2 times 1/6 times 3x plus 2 times the derivative of the inside times 3. Therefore, notice that we're going to get that the derivative is going to equal 3x plus 2, which again is f of x. Okay, so the next slide is example 14.19, and they want us to find the area a of x between the graph of the function f of x equals x plus 2 and the interval -1 comma x. and then find the derivative of a of this area function. Okay, so notice that at -1, now let's, if this is -1 here, the y-axis should be around here somewhere. So notice that this is not an x-intercept. So the height at x equals -1 is going to be 1. How do we know that? Well, because if this is f of x, notice that this point here, if we want to find it, all we have to do is f of -1. And f of -1 is equal to -1 plus 2, which is 1. So that means that at this point, this height is 1. Then the base is obviously going to be x plus 1 again, right? Because this is 0, 0, so there's a distance of 1 plus x for the base. And then the height is simply going to be f of x itself, which is x plus 2. So in order to find the area function, we have to take into account that this is not a triangle, but rather a trapezium. And remember that for a trapezium, the area is equal to the sum of the bases times, or 1/2 the sum of the bases times the height, right? So this would be 1/2 times the sum of the bases. Now we have to consider this here and this here as the bases of the trapezium. So it would be 1 plus x plus 2. This would give us the sum of the bases times the height, which in this case will be x plus 1. X plus 1. And then this is simply going to be equal to 1/2 x plus 3 times x plus 1. And then we get that the area function is going to equal, this will be in the end 1/2 times x squared plus 4x plus 3. So this is the area function that will give us this area here. Then if we want to find the derivative, notice that it's simply going to be equal to 1/2 times 2x plus 4, and this is going to be x plus 2. So again, we're going to get f of x when we do the derivative of the area function. So notice that in all the three examples we did previously, we had the case that the derivative of the area is equal to f of x. So in general, what this means is the following. If we have a curve that is continuous, so let's make a curve that is continuous here, and we find the area under that curve from A to a value x and this curve is f of x here. So if this area here is a of x, then if we do the derivative of that, we're going to find the upper boundary of the region, which is the graph of f of x. And this intuitively, what it does is give us the fundamental theorem of calculus, which says that if the area under a curve is equal to the integral of f of t dt. Now this is a function of x. Although it's in terms of t, it's still a function of x. So the integral from a to x would give us the area under the curve. So that means that the integral from here to here would give us this area. But if we do the derivative of that, we're going to get the original function. So basically what this is saying is that the derivative and the antiderivative or integral are the inverses of each other. So next we have some basic properties of the definite integral. One very important property is that if you have the integral of f of x from a to b, this is equal to minus the integral from b to a. This is a very fundamental property that you will find is very useful. Next, that we have that the integral of f of x from a to a is obviously equal to 0. Now, why is that? Well, if you're integrating from a to a, that means that you're not really moving, you're not finding any area. So this would just be 0. Next, we have the case where if you have the integral of any constant k from a to b, that is simply going to be k times b minus a. We can see this graphically in a very easy manner. So if this is the x-axis and this is the y-axis, and you have some constant k, so this is f of x equals k, then if you want to find the area under the curve between a and b, this is obviously simply going to be k, which is the height, times the distance between a and b, which is simply b minus a. So this is just simply finding the area of a rectangle. This property is also, the next one is the same property that I showed you guys with indefinite integrals. If you have the sum of two functions in an integral, you can separate it, right? The sum or the subtraction. Also, you have the case of a function where you have a constant. You can take that constant out of the function, out of the integral, and multiply the integral by that constant. And finally, this one is interesting. If you have a point C in an interval between A and B, then you can say that the integral from A to B of f of x is the same as the integral from A to C plus the integral from C to B. And that just means that we're adding this area plus this area is equal to having the whole area between A and B. Okay, so next we're going to look at something called the average value of a function. This is also known as the mean value of a function. And if you have a function and an interval that goes from A to B, we can find the average value, which would be this point here, by performing the following operation. You would go 1 over b minus a times the integral from a to b of f of x dx. Now f of x is obviously this line here. And what this is going to do is give us the average f of c, which is again this point here. Now notice that small cap f of x is this function here, but the antiderivative of f of x is known as capital F of x. So this would be the antiderivative of f of x. And then if you find the antiderivative and plug in b and then subtract from that the antiderivative and plug in a and divide that by b minus a, you're going to get the average value. Now notice that the interesting thing with this is that with the average value, we can find an area that is equal to the area under the curve by finding the area of this rectangle. So in other words, the area of this rectangle, whose height is f of c, is equal to all the area under the curve in the interval between a and b. Okay, so next we're going to talk about the first fundamental theorem of integral calculus. Now remember that the integral, the definite integral of a function is going to give us the area under the curve between the bounds, right? The lower bound a and the upper bound x in this case. So for example, if we have a curve, the only condition is that this curve be continuous, right? So if we have a continuous curve between a and say another interval or another endpoint of the interval b, and then we have some other point here x. If we want to find, and this, let's say this is t, this is y, and the function would be f of t. So if we want to find the area under the curve f of t between a and x, which is this area here, we would simply have to do the integral, the definite integral of f of t dt between a and x. But what happens if we have a distance here, let's say h, so this here would be x plus h. And we could say likewise that the area between a and x plus h, so all of this here, all of this area, would be equal to the definite integral of f of t dt between a and x plus h. But now we want to do something here, which is to find the derivative of a. So notice that if we use the definition of derivative with limits, recall that it's the limit as h approaches 0 of a of x plus h minus a of x over h. So recall that we're trying to find the derivative of the area function by using the definition of derivative with limits. And recall that it is the limit as h approaches 0 for a of x plus h minus a of x over h. But if we analyze this upper part here, a of x plus h minus a of x, notice that from before we know that a of x plus h is equal to this integral here, right? This integral here is the area under the curve between a and x plus h. So that first integral represents all of this area here, all this area under the curve between a and x plus h, minus a of x, and we said that a of x would be the area under the curve between a and x. So I'm going to mark it in red here, and it's going to be this part of the area here. Okay, so if we do some rearranging, notice that we can rewrite this here. I'm going to erase so you can see a little bit better. Notice that we can rewrite this as a positive if we switch a and x, right? So notice that here we have a switch. Now x is the lower bound and a is the upper bound, and we can switch the sign from negative to positive. Recall that that comes from the property that if you have the integral from a to b of f of x dx, that is equal to minus b to a of f of x dx. Okay, so algebraically, once we have that, notice that here we have an interesting situation because now we have the sum of the integral of f of t dt from x to a, and then from a to x plus h. And this is the same as saying the integral from x to x plus h of f of t dt. That also comes from the property that we saw before, where we said that if we have a midpoint c, remember that if c is between a and b, then the integral from a to c of f of x plus the integral from c to b of f of x dx is equal to the integral from a to b of f of x dx. So that's what the property that we're applying here algebraically to get to this. What does it mean graphically? Notice that in the beginning we said we're doing the area, just speaking of areas, we're doing the area a of x plus h minus a of x. So the area under the curve that represents a of x plus h, we said was all this, right? We're going to erase this here, but that area, that whole area is all of this, right? From a to x plus h. That's what that integral gives us, all of this area. But if we subtract, what happens if we subtract this part? If we subtract this part, what are we left with? Right? If we subtract from a to x, well, we're only going to be left with this over here, this part over here, from x to x plus h. So graphically, that's what we're doing. We're just finding this area. So that's what this represents. Both, we can see that both algebraically from this, and we can also see it graphically up here. So we're left with this area. That's going to be for the top. This is in order to simplify the operations we're going to do. So once that we have understood where this comes from here, we can bring up the next part of the slide. And notice that this is again the derivative of the area function using the definition with limits. We would arrive to this expression here, the limit as h approaches 0 of 1 over h times the integral from x to x plus h of f of t dt. So from the average value of f of x, notice that this is the same as the average value function. We can conclude that there's a point C that belongs to the interval such that f of c is equal to this, right? 1 over h times the integral from x to x plus h of f of t dt. So what happens to c as h approaches 0? As h approaches 0, x plus h must approach x. So that means that we're squeezing c between x and a number approaching x, right? So because this is the mean value, if h gets smaller, x plus h starts getting closer and closer to x. Therefore, c also gets closer and closer to x. So notice that that means that the derivative of the area function gets to this, and because of the mean value theorem, this is going to equal f of c, which at the same time is going to be equaling f of x. So in other words, what it's saying is that if we do the derivative of this integral from a to x, we're simply going to get f of x. So this is the very powerful statement that is known as the first fundamental theorem of integral calculus. And in essence, what it's saying is that the process of integration and differentiation are inverses of one another. So now we have example 14.20, where they ask us to find each derivative. So notice that this is simply an application of the first fundamental theorem of integral calculus. So for A, it says derivative of the integral from negative e to x second squared of t dt. So this one is a direct application. We don't really have to do anything except plug in x instead of t, and that would give us the result. Now the important thing here is that the lower bound has to be a constant, which we have, and the upper bound has to be in an x preferably, or at least an expression in terms of x. So this is very straightforward, and we're simply going to get that this equals second squared of x. With b, we have a similar situation because it's also straightforward. So we have the integral from 0, which is a constant, to x of dt over 1 plus t to the 4. This is simply going to equal 1 over 1 plus x to the 4th. Okay, but how about c? That's what we're going to do next. So for c, notice that they also ask us for the derivative, but in this case, the integral has a lower boundary of x and an upper boundary of pi. and this is 1 over 1 plus t to the 4 dt. So what we need to do is switch this and this. But remember that we can swap that by simply putting a negative sign. So we can say that this is the same as the derivative of minus pi to x of 1 over 1 plus t to the 4 dt. And now we can just simply substitute. But now this is going to be negative 1 over 1 plus x to the 4. So next we have d, which wants us to find the derivative from 0 to 2x plus x cubed, and the same function inside, which was 1 over 1 plus t to the 4 dt. So notice that in this case we do have a lower limit that is 0 or a constant, but the upper limit is in terms of x, but it's not simply x, so we're going to have to find the derivative of this. In other words, this is going to equal, nice and straightforward like before, it would be 1 over 1 plus the upper bound, right, t to the 4, so it's going to be 2x plus x cubed, this to the 4, times the derivative of this, which is going to be 2 plus 3x squared. And we're going to simply get 2 plus 3x squared divided by 1 plus 2x plus x cubed to the 4. And you can leave it like that. You're not expected to expand this part. Okay, and finally we are going to do E, where they want us to find the derivative of the integral from x to 2x plus x cubed of 1 over 1 plus t to the 4 dt. So notice that we don't have a lower bound that is a constant, but we can play around with this and say that this is the same as the derivative of x to k, right? Supposing that k is a point or a constant that is between x and the expression 2x plus x cubed. So from x to k of 1 over 1 plus t to the 4 dt plus the integral from k to 2x plus x cubed of 1 over 1 plus t to the 4 dt. So notice that we almost have the circumstances that we require in order to be able to solve this derivative. The only thing is that the upper bound here is a constant and the lower bound is x, but we can switch that by putting a negative sign in front of this. So if we put a negative sign in front of that, we can switch x and k. And with that, we're ready to apply the first fundamental theorem of integral calculus. So notice that this is simply going to be, and I'm going to put this first here, this expression first, which is going to be exactly the same as what we got for an answer in part D. As you recall, that was 2 plus 3x squared over 1 plus 2x plus x cubed to the 4. And then minus, which would be this part here, minus, simply we need to write 1 over 1 plus x to the 4. So next we're going to take a look at the second fundamental theorem of integral calculus. So recall that we said that the area function, a of x, is equal to the integral from a to x of f of t dt. Then we have that if capital F of x is any antiderivative of f of x, then applying what we learned earlier, we have that f of x, capital F of x, is equal to a of x plus c, where c is an arbitrary constant. So what happens if we do a of b, right? A of b. Well, we can say that f of b, capital F of b, is equal to a of b plus c. And this is the same as saying the integral from a to b of f of t dt plus c. Notice that all we're doing is substituting x with b in the area function. Okay, if we do f of a, that's going to be a of a plus c, and it's going to be the integral from a to a of f of t dt plus c. But this is the same as saying 0 plus c, because remember that if you have an integral from a to a or from one constant to the same constant, that's just going to equal 0. So then if we subtract these two expressions, if I subtract this from the top expression, I'm going to get that f, capitalized F of b minus capitalized F of a, in other words, the antiderivatives. This is going to equal, and remember that this is just going to be this, this we can eliminate, we can forget about it. We can just go this minus 0 minus c, so we're going to get the expression integral from a to b of f of t dt plus c minus c. But this cancels out, so notice that we have the second fundamental theorem of integral calculus, which is saying that the solution to an integral that is bound, right, that has a bound a and b, is going to simply be the antiderivative of f of x, and then we plug in b into the antiderivative and subtract the antiderivative when we plug in a. And we're going to see this in some examples. So in example 14.21, they ask us to evaluate each integral. Okay, so a would be the integral from -1 to 3 of x to the 5 dx. So the antiderivative of this is obviously going to be x to the 6 over 6. So the notation for this is normally a straight line, and we put the lower bound down here and the upper bound here. And then we have to do the part of, remember, f of b minus f of a. So that's going to be here 3 to the 6 over 6 minus -1 to the 6 over 6. So notice that I'm just plugging in 3 and then subtracting and then plugging in -1. So if we do the math here, this is simply going to give us 364 over 3. So for b, they ask us to find the integral from 0 to 4 of the square root of x dx. Remember that we can rewrite this as the integral from 0 to 4 of x to the 1/2 dx. And then if we integrate this, it's going to be, remember that we have to add 1 to the exponent, so that's going to be x to the power of 3/2 and divided by 3/2, but that's the same as saying times 2/3, right? And then the interval from 0 to 4. So this is going to equal 2/3 times 4 to the power of 3/2 minus 2/3 times 0 to the power of 3/2. And then this is simply going to equal 16/3. So next we have C, where they ask us to integrate for cosine of theta from pi to 2 pi. So remember that the antiderivative of cosine is simply going to be sine. So it's going to be sine of theta from pi to 2 pi. And this is going to be simply sine of 2 pi minus sine of pi. But remember that this is equal to 0, and so is this, so this is going to equal 0. So you might say, how can the area under the curve of cosine between pi and 2 pi be equal to 0? Well, remember that this is a sinusoidal function, and that, let's say we have a graph here of the cosine function. So remember that cosine of pi, what's cosine of pi? Cosine of pi is -1. So if this is cosine and this is -1 here, cosine of pi is -1. So that means the graph goes here. Then it would go up, go through 0, and that's when we have a 3 pi halves, and then it would go up to 1, which is cosine of 2 pi. So notice that these areas would cancel each other out, because this area here, since it's under the x-axis, is considered negative, and this area here above the x-axis is considered to be positive. So these two values would be equal and opposite, therefore they would cancel out, and we would get a total area under the curve of cosine of 0. So now we're going to do D, which is the integral from 1 to 2 of 4 plus u squared over u cubed du. So the first thing you can notice is that we can split this into two separate integrals, right? So notice that the first one would be 4 times the integral from 1 to 2 of u to the minus 3 du plus the integral from 1 to 2 of 1 over u du. And then this is simply going to be 4 times u to the minus 2 over minus 2 plus the natural logarithm of the absolute value of u. And the interval would be from 1 to 2. So then all we have to do is plug in the values and solve. And we're going to get that this is equal to 4 times 2 to the negative 2 over negative 2 plus the natural logarithm of 2. We don't need the absolute value because this is positive. Minus, and here we're going to need a parenthesis, 4 times -1 to the minus 2, this over negative 2, plus the natural logarithm of 1. And then from here, we're going to get -1/2, which is a result of this, plus natural logarithm of 2, and then plus 2, which we get from here, because this will be -2 and there's a negative in front, minus natural logarithm of 1. But recall the natural logarithm of 1, and by the way, the logarithm, any logarithm of 1 is simply 0, so we can forget about that last part. And then all we have to do is add the -1/2 and the 2, and this is going to equal to 3/2 plus the natural logarithm of 2. Okay, so here we are in example 14.22, which will be the last one on this video. And they ask us to evaluate the integral from 2 to 6 of the square root of 4x plus 1 dx. So here we require u substitution. So let's say that u is equal to 4x plus 1. Therefore, the derivative of u is going to be 4 times dx. So notice that we don't have this 4. Therefore, we're going to have to add that to the integral. And we can do that by saying 1/4 times the integral, right? But there's something else that we have to be careful with, and that is the bounds, because once we do u substitution, the bounds will change as well. We have to plug in the values into the u function. So u of 6 is going to equal 25, and then u of 2 is going to equal 9. So those are going to be the new bounds of the interval. So again, we have to remember that we also need to multiply by 1/4 in order to be able to do the integral. So we're going to have 1/4 of the integral from 9 to 25 of u to the power of 1/2 du. Notice that we're just substituting 4 dx, right? Because if I have here 4 dx, the 1/4, this is just du. So that's why I get this expression. And then from here, all we have to do is integrate this. And this is going to be equal to 1/4. And it's just the same as usual. Adding 1 to 1/2 is going to give us u to the power of 3/2. And then we divide by 3/2, which is the same as multiplying by 2/3. And notice that this is going to be the same as, we cancel this out, we get a 2 here. This is going to be the same as 1/6 u to the power of 3/2. And we have to integrate from 9 to 25. So this is going to give us 1/6 times, in this case, 25 to the power of 3/2 minus 9 to the power of 3/2, right? And then this is going to give us 1/6 times 125 minus 27, and we're going to get 49/3.